I just started the recording, so make sure to not only click on that, but also click on your slides too. It kind of puts it into a limbo because just make sure your slides are selected. Because when it asks you the prompt like yes, when you click that, it like puts you in this limbo in between the Zoom and like your slides, but it should work now.
Okay, it's working.
Great. Just wanted to make sure. Thanks.
Great. What?
Oh, so you arrived yesterday?
Yeah, yesterday night.
Oh, okay.
But everything was very
Is it
small.
direct flight from Chicago?
Yeah, to Europe. And then
And then you took
I took an Uber here.
oh, okay.
Yeah. I mean, I arrived, I mean, and the security guy was here and he gave me the key and everything worked well. So, and the accommodation is very nice, I have to say.
Oh, really? Where is it?
I don't know, it's like one of it's the visitors' houses. It's in Springfield.
Is it far from here?
No, it's like 5 minutes walking.
Oh, okay.
Very close. Yeah, and I think, I mean, it looks like kind of like a small apartment. Honestly, I mean, there's like a small kitchen, living room. I think it's maybe they use this more for long-term visits. I don't know. But
You can have breakfast and lunch and inside here.
yeah, I had a breakfast here this morning.
Okay, that's nice.
Yeah, because it's true, like there are no many.
And they have a small shop.
Hello. Good.
Long time no see.
Yeah, I know. It was 2018. I was trying to remember.
Names, right?
Yeah.
I believe, or
Yeah,
one of these European conferences.
Yeah, it was in mind. Yeah. Summer program.
Maybe at the beginning, let me first ask the audience if you're okay, if you're comfortable with Jose like speaking without his mask. Right? So I guess you can.
Okay.
Okay, so maybe I'll just start the introduction. So today we're happy to have Jose Maria Ezquiaga from Chicago. So Jose obtained his PhD in 2019 from the Autonomous University of Madrid with Juan Garcia de Lida. And now he's, as you can see, the Einstein NASA Fellow at the University of Chicago, and he's going to enlighten us on cosmology with compact binary coalescences. So, then please take it away.
Thank you, Misa. I'm really happy to be here talking to you about research I've been doing at the University of Chicago. Please feel free to stop me at any point. I'm very happy to take questions during the talk. We can just keep this very informal. So it's certainly a very exciting time for gravitational wave astronomy. In just 5 years, I mean, since 2015, the first detection, now we have more than 100 events. We've seen binary black holes. Most of our events are those, but we have also seen binary neutron star black holes. So we are starting to have like a really rich collection of compact binaries that are enlightening us about the many astrophysical processes. But for the talk today, I want to focus on what information they can give us about cosmology, what can we learn about the large scale structure of the universe, the laws of gravity, and related topics. Also, I think it's important to keep in mind for this talk is that although we are all very excited with our 100 so detections. This is really just the beginning. So to show that, I like to plot the number of gravitational wave detectors as a function of time here on the left, and also the horizon redshift, how far our detectors can see as a function of the total mass of the system. So you can see that now we have, again, like 100 detections, mostly systems with, we are mostly sensitive to systems with total masses of around 100, and which are below redshift 1. But with our current detector technology, what is currently called 2G, second generation, in the next two plan observing runs, 04 and 05, we will move to hundreds and thousands of detections, and we will reach redshift around 0.1, around 1, sorry. But the biggest revolution will come with the next generation gravitational wave detector, 3G, which is going to provide us hundreds of thousands, if not millions of detections per year. And you can see also on the right that you are essentially covering all the cosmic history, like you're going to redshift of larger than 10. So for most of the formation channels that we expect, we are going to see all the events. And in addition to what we can do from ground, there will be also LISA from space, which is has much larger arms and therefore detects lower frequencies. So it covers mass range much heavier, typical, I mean, most sensitive to binaries of 10 to the 5 solar masses. So you see that in the future, we are really moving towards being sensitive to high redshift and also having a lot of events. So the question is, what can we do with all these events at high redshift? And also, of course, we are seeing farther away, but all the events which are closer will be seen with higher signal to noise, which is important if we want to, for example, see distortions in our signals. Also, we will have better constraints on polarization, better constraints on localization, just because our network of detectors will also increase. So now we have three, well, the two LIGOs, Virgo, and then Cagra is starting to join us, not yet at full sensitivity, but in the near future, we will improve a lot on that. Now, so that's the big picture of what we will see. Now, in simple terms, when a binary coalescence, it emits a gravitational waves, which travels across the universe, and then this signal is sensitive to the expansion of the universe. What we detect essentially from this signal when it arrives at our detectors is just the luminosity distance, which comes from the inverse of the amplitude. We just have a spherical wave, which as propagates, its amplitude decreases with distance. And we also detect redshifted masses just because as the universe expands, the signal gets stretched, gets redshifted. So these are our two observables, right? So if we want to think about cosmology, of course, the obvious thing is to focus on the luminosity distance, because this is what is provided for us for free with the gravitational waves. What gravitational waves do not provide is information about the redshift. So if we want to do cosmology, the most direct way is if we were to identify an electromagnetic counterpart, what is called as bright sirens, because from the electromagnetic counterpart, you can get information of the redshift, for example, identifying the host galaxy, and then you can constrain the expansion rate. Notice that for this to have electromagnetic counterparts, you really need to have some matter around the compact binary. So you need to have essentially neutron stars, or having the black holes merging in an environment. Something important for the future is that is to realize that, I mean, that it might be challenging to detect this counterpart at high redshift. So now, binary neutron star will be very good to constrain the expansion rate at low redshift, not so good at high redshift. But there are also alternatives, because if you, with the gravitational wave, since you have a network of detectors, you know more or less where it comes in which region of the sky. You have an error in your luminosity distance. This gives you a volume. So you can say, okay, how many galaxies are in this volume? My gravitational wave has to come from one of these galaxies. So you can statistically infer the redshift of the source just by making that assumption. And this is what is known as dark sirens. And there are examples of that. For example, using the dark energy survey catalog. Now, the problem here, or one of the limitations, is that for this method to work and not to be biased, you need to have complete galaxy catalogs. And also you need to have like a small localization, because otherwise you have so many galaxies that there is no real inference that you can do. So this is essentially the two main methods to do cosmology that has been used so far. Now, when you fix your cosmological model from our observables, redshifted masses and luminosity distance, you can directly obtain redshift and masses. So just if you fix cosmology, you can get those, and then you can constrain, for example, the merger rate as a function of redshift, or the mass distribution of your binaries. Now, there is a third method to do cosmology, which is a combination of the previous two, and it's what we call a spectral sirens. And this is just by noticing that, as I was saying, we are sensitive to redshifted masses. So if we identify or we know a reference mass scale in our mass distribution, we can follow this reference mass scale at different luminosity distance scales. So this will be providing us redshift information, just because cosmology is only shifting the reference scale in a very concrete way. So for this method to work, what you need to have some features in your mass distribution which are easy to identify. And notice here that this is a completely like data-driven problem, in the sense that you want to see features at low redshift, and you want to follow them, but you don't need to. I mean, you can use a parameterized model, but you can also do this just simply directly analyzing your data.
Sorry, and the assumption here is that the physics doesn't change.
Yeah, so that's a very good point. Essentially, for this to work, you need your mass scale not to change with redshift, but even if it changes, as I will show, you can break the degeneracy. So that's an excellent point. But the key thing is that cosmology will do something very different to the mass distribution as an evolution of the astrophysical properties will do. But it's a good point. Right. So when thinking of this method, which will be the focus of the first part of the talk, this spectral siren method, we need to understand what we are seeing in our data, right? So this comes from the latest LIGO catalog. This is the mass distribution. This is M1 of the primary mass. And these are different models that the collaboration has used. I don't want to enter into the details of these models, but for us, what it will be important is like the broad features that we can see here. And something which we are seeing is that, first of all, around 40 solar masses or so, there is a break. So our rates of binary black holes drop beyond that point. There is the question of whether after that point we really have a gap, or we don't have, and I will comment a bit on that later. But at least the break is something which is very solid in our data, and especially because this is the mass range where we are most sensitive to. Notice also that this is the y-axis, which is the rate, is in logarithmic scale. So your rates are really dropping. So this is a sharp feature. And then the other thing that we see is that there is more or less there seems to be a maximum around a bit above 10 solar masses. But to see, in fact, this lower mass part, what we have to do is we need to study this mass distribution in conjunction with all the low mass binaries. And this is the equivalent plot for this mass region. Now, in the x-axis, it goes from 1 to 10. So it encompasses binary neutron stars and low mass black holes. And here, what we can see, which is also a very robust feature, is that there is a clear drop on the rate at around 2.5 solar masses. So what this is telling us is that with a single mass distribution, we cannot fit binary neutron stars and black holes, which is something which was somehow expected, but at least it's also good to see in the data. So we can see that the rate of binary neutron stars is definitely much larger than the one of binary black holes. I mean, it just so happened that because they are lighter, the volume that we can observe is smaller, so that's why we have just a few binary neutron stars, but the intrinsic rate is much larger. The other thing here, which is interesting, is whether there is some sort of gap between binary neutron stars and black holes. And this is something which data, again, cannot tell us yet, cannot robustly tell us yet. But for some of these models, there might be some hints, but it's not robust.
But do you incorporate any sort of cutoff for the neutron star maximum?
No, so this is this analysis is with you don't care about you don't label, if you want, the compact binary. So this is just you don't distinguish between binary neutron stars and black holes.
But would your results change if you artificially were to put a cutoff in, let's say, at 3 solar masses? If you say, well, above that, I don't have neutron stars, I assume that there's some.
Right, yeah. So you can do an analysis in which you treat differently each of the populations. And I believe now that you mentioned this, I think this multi-source model, I think that is treating differently the neutron stars from the black holes. Yeah, so you can do that. Yeah, but the thing is, like at these lower masses, we are much less sensitive yet. So that's why we need to wait essentially to zoom in that region.
So
Yeah.
For the low mass end, is there any constraint from short gamma ray burst?
Yes. So with short gamma ray bursts, you can also do population analysis. But I think I mean I have colleagues in Chicago, Mike Sevin, who is he's actively working on this, but I'm not sure if there are I don't know now, like published work related to that. But of course, if you assume that all short gamma ray bursts come from binary neutron stars, you can do some population analysis. I think there is some work. I can later search it for you. Yeah.
Sorry, so the features obviously is also model dependent, right? Depending on what model you put in, sometimes you have a bump, like
Yeah.
So what is the robust way of testing that a feature is a real feature? Is it just having multiple models, and if all of them have a feature, then you
that's an excellent question, and because like just because we have a finite number of events, you will have a statistical fluctuation that will make dips, and I think we are also again working on some of these things, and within the collaboration it was also being tested. I think, like for example, this break here is very robust. So it's something that you see in all the models, and you don't get these dips here, and these are totally model dependent. Right? Yeah. Any more questions? Good. Yeah. So something that I wanted to mention also is that this possible gap is potentially very interesting, because it's something which is consistent with the theory of period-stability supernova that predicts that you cannot form black holes beyond around 50 solar masses, just because the core is so hot that then you trigger electron and positron annihilation that makes a runaway process that ejects all the material. But this is an effect that only lasts for a certain mass range. So this means that above more or less 120 solar masses, it's also possible to form binaries, sorry, to form black holes just from isolated stars. And then what I wanted to point out is that now we are mostly sensitive to whatever is below this gap, if there was to be a gap. But in the future, we will be able to probe this other side if it's there. I'm not saying it's there, but if it's potentially there, that will be very interesting because this will give us like another reference mass scale, and also it will provide us like evidence of this gap. And these binaries, what we call them far side binaries, are very interesting also because they are perfect target for multiband detections, that is events which are seen first in the spiral with LISA from space when it flies, and then it will merge in the band of ground-based detectors. So that's interesting because you can do much better parameter estimation. So if these fast side binaries are there, this population is there, it will dominate the multiband detections, which is something cool. Now, so for what comes next, I'm gonna just take like a very simple toy model representation of some of the hints that we have been seeing. And if there were to be like this neutron star black hole gap and this spin instability supernova gap, what this will mean is that our full distribution of compact binaries will have at least 5 independent scales. And this having these 5 independent reference mass scales is very important, as we will see in a second, because when you want to distinguish from astrophysical evolution, just tracking the different parts allows you to break some of the degeneracies. Something here to notice, so yes, so something here to notice, the thick lines corresponds to the source population, and then the dashed line corresponds to what you would detect with second generation detectors, and the solid thin lines corresponds to what you would detect with third generation detectors. So what you see is that you can notice that, again, as I said before, the rate of binary neutron stars is much larger, the intrinsic one, but with second generation detectors, our selection bias makes that we only detect a lower fraction of them. And also this is even more relevant when you think about how many of those you detect as a function of redshift. So that's the panel below. So the different colors indicate different redshift beams. So you see, for example, that binary neutron stars with second generation detectors, essentially you just only detect them below redshift of 0.5. So that's what I was saying also, that with binary neutron star is something more to measure like the local expansion rate. And you can see also that for second generation detectors, the dashed lines, you are more sensitive to higher masses. With third generation detectors, essentially you are sensitive to all the masses equally and all the redshift equally. So these changes in the overall rate is just a matter of the merger rate history being different. So here I'm assuming that these binaries follow the star formation rate, but that's, yeah. So for what comes next, what I want to do first is just from all the things that you can do of test of cosmology, I will focus on lambda CDM and see how you can constrain the cosmological parameters. And in particular for us, what I will be assuming is that we are in a flat lambda CDM cosmology. So we will be focusing on H0 and omega matter. And when you do this, you can do some estimates of how well you could constrain the expansion rate using this spectral siren method. So on the left, we have the estimated error on of the Hubble expansion for second generation detectors, on the right for third generation detectors. And here, these different color lines comes from the different scales of your mass distribution. So you see that with second generation detectors, the best constraints come from the lower end of the peninstability supernova gap. So binaries around 50 solar masses, this break in the mass distribution is what is going to give us the highest constraints, which are can be better of 10% at around redshift of 0.7, and this is consistent with previous work. Now, when you move to third generation detectors, things changes, because since you are now sensitive to all the binaries, you are more you can see like the higher rate of low mass events, and that's why the neutron star black hole gap, if it's there, these edges of this gap would be what will dominate the inference of third generation detectors. So the picture will change. Now, coming to the question of evolution, of course, it's clear that we need to understand what happened when our mass distribution is changing. So the first thing to notice is that cosmology, so this is, by the way, sorry, the detected distribution as a function of redshifted masses. So this is different from before. Before I was always showing the source frame masses. This is redshifted masses. So now, focusing only on the distribution of black holes, the point is that cosmology is going to do something very, very simple. It's just going to shift all your masses because it's multiplying just 1 plus c. So when you are doing you are plotting in log scale, you are just shifting, and then depending on depending on your cosmological parameters, the shift will be faster or slower. So, for example, this thick line on the top panel, this is a low redshift luminosity distance beam. The thin lines are a higher redshift luminosity distance beam. And then you can see that if you change H0, you are just changing how much you shift your distribution. But you are shifting all the scales. So whatever cosmology does has to be equal for all your scales in the mass distribution. So that's why it's important that you identify different mass scales and you analyze them all together. Now, if you think of what a mass evolution could do, this is of course very uncertain. It depends on the formation channel, the models you have. As a toy model, let's imagine that one of our edges, in this case, this maximum mass, is evolving linearly with redshift. So if this maximum mass is evolving linearly with redshift, you can see that when you go to the luminosity distance being at higher redshift, in the higher masses, you can have something which looks like cosmology, right? But which hints that there could be some degeneracies. But then, of course, if when you go to the lower masses, because in this toy model these are fixed, you see that that you can is very different from what cosmology will do. Now, so the first point is that for cosmology to be degenerate with mass evolution, you need to shift all the masses, all the reference mass scales. And the second point is that you need to shift this reference mass scale at the same rate that cosmology predicts. And here I'm saying cosmology always implicitly meaning lambda CDM, but just to clarify, so this is, for example, the expansion rate as function of redshift. In the top panel, the shaded bands corresponds to changing H0 and omega matter. H0 is just rescaling our Hubble parameter. Omega matter changes our Hubble parameter when we are at higher redshift. Now you can compare this to what you would infer if you were to focus only in this. If you focus only on this mass, on these high masses, and you analyze this without taking into account the mass evolution, then your redshift will be biased just because it is shifting with gamma. So this is introducing a bias in your redshift, and these are the consequence of this bias are the dashed lines. So what you see, for example, is that in this very simple toy model, but I think it can be extrapolated in general, is that as you move to higher redshift, like the bias that you will introduce with this mass evolution will be very different to what cosmology will do. So to have a true degeneracy between cosmology and mass evolution, you need to A, shift all the masses of your distribution, and B, shift them at the same rate that cosmology does. So that's why we are optimistic, at least, that this method of spectral sirens can be useful in the future. Of course, there will be some degeneracies, smaller one, but not big ones can be at least broken.
How are you inferring the evolution? Are you assuming like it's coupled to star formation?
Yeah, so the merger rate is following the star formation rate. Yeah, and then I'm assuming just that this linear evolution in the mass of on the maximum mass.
So how good is this like the assumption that it follows star formation rate? So if the source are coming from like the center of global clusters, then probably that will follow star formation rate that much.
Yeah. So that's a good point. I think the conclusions will hold in the same way, but yeah, you're right that the merger rate from clusters is a bit different. I mean, they both peak more or less redshift of 1.5 or so. So I mean, I don't know. I mean, they both increase and they both decrease above redshift of 1.5. The details are different, yeah, but I don't think for this message that will change. I mean, the details of the curve, I think yes, but broadly speaking, no.
But so I don't understand. So let's say you take one of the scales, right?
Yes.
So cosmology just does 1 plus z times the mass.
Yeah.
The other thing maybe does some other function of z times the mass.
Yeah.
So let me expand this function and say it's some 1 plus z and then 1 plus z squared, 1 plus z cubed. So there's always an unknown part proportional to 1 plus z, perhaps. I mean, if you don't know the physics, how can you distinguish? I can understand that the things that look like 1 plus z squared is not cosmology, and so maybe you can tell, but the 1 plus z, how can you ever break the degeneracy?
Right. So I think what you can see in this plot, like when you are at low redshift, like the difference are smaller. So it's when you start moving close to redshift of 1, where of course, like these terms which go beyond the 1 plus z term are when it's relevant. But at very low redshift.
But you've assumed a particular form here, but if it was an arbitrary function,
yeah,
then wouldn't it just be impossible to break this degeneracy? If you allow yourself any function,
no,
a little bit of this function can look like the cosmology. Well, why not?
Yeah, no, a little bit, yes. Yeah, a little bit, yes, I agree. But then you need also, so I think this slide and the previous one together is important, because like it's not only one mass scale, it's all the mass scales. So like if all the mass scales are moving in the same way, I mean, you have a bit of the degeneracy, but like if typically, I mean, we expect like different parts of the mass distribution will evolve with redshift in a different way. Also because you can have contribution from different channels. And so
yeah, so I would say that the way each of the mass distributions, let's say, evolves, each of the cuts or whatever,
yeah,
shape, is an arbitrary thing that you don't know, because one comes from physical process, unless they are coupled because of the same physical process,
yeah,
and the same channel,
yeah,
for sure that you know this for some theorem or something. Otherwise, it's physical process one moves this one, physical process of which you don't know very much.
Yeah.
About. So I'm surprised that you have so many freedom that you can actually break this degeneracy if you don't have some form that you assume like that, like gamma and z.
Well, we have not done the test of doing an completely non-parametric analysis, so that's true. I think I would expect that you could still this conclusion will hold, but I have to admit also that we have not done the full non-parametric analysis. So So now like going to a concrete example, we can think of a situation of next generation detectors. Let's have like 10,000 binary black holes. This corresponds more or less to 1 month of data. And then you can do Bayesian inference of these population, astrophysical population, and cosmology at the same time. So then, of course, if when you are doing your analysis, you don't include, so here we have the posteriors for omega matter and it's not, and then we have different colors corresponds to different mock populations. So we are just simulating a different population of black holes. The blue one, there is no evolution at all. The green one, there is only evolution in the maximum mass, and in the green one is only evolution in the maximum mass, and the red one there is evolution in both maximum mass and minimum mass. And then we are doing the Bayesian inference in a model in which we don't include evolution. So we only put astrophysical parameters and cosmology. So then what you can see here is that, of course, if in the case in which in the red posteriors, you are completely biasing your cosmology just because you are not taking into account this evolution. Now, it's interesting that for the case of the green one, you are biasing a little bit, but not much, just because in this case, you're only shifting one of the peaks, one of the edges. So the fact that your minimum mass is fixed, and the fact that we are more sensitive with third generation detectors to the minimum mass of the black holes, this means that this makes the analysis not to be biased. And then in the case of when there is no evolution, since the mock population is the same as the one that is being analyzed, you get like something which is consistent, completely consistent with the input model.
Sorry, I'm missing something very basic. How do you infer omega dark matter?
How do I?
Omega M is dark matter.
Yes.
Correct. How do you infer that from?
So it's just the two parameters. I'm parameterizing the expansion rate, H of C.
Oh, I see.
With these two parameters, and H of C comes into a luminosity distance. Yeah, I'm assuming lambda C. Yeah, exactly. Yeah. So if you repeat the analysis and then you allow for to evolution in your model, and here again we are doing this parameterized analysis. But still, what you can see is that now, when you include evolution in the analysis, you can recover well both cosmology, and you can also measure the evolution.
You assume some of these scales that you assume were pretty sharp things.
Yes.
Is this helping? Meaning, if it was some smooth thing, would your number?
Yes. So these numbers that I'm saying, you should take them as a order of magnitude, but I think. It's been shown, and we have tested, like it's maybe changing like factor of 2 or 3. It's not going to change like a factor of more than, I mean, the order of magnitude is correct, but yeah, it's true that if you have a sharp feature, that helps you with helps with your analysis. So the sharper the better, but is not. I mean, at the end you have so many events, and this is also again 1 month of data. Like, I mean, when you accumulate a full year, for example, or several years, you can do better. But yeah, that's a good point. So at the end, what we see is that, I mean, the order of magnitude of the error that we can get in the expansion rate with third generation detector is something which is pretty impressive. It can be sub% within only 1 month of data. And you can also, and the nice thing is that you are also sensitive to this high redshift, and you can compare this on the right, for example, with the forecast of DESI, and you can see that it's of the same order of magnitude, if not better, at high redshift. So gravitational waves with the next generation detectors are really like a very clean sample to understand cosmology at high redshift. Now, just very quickly, I just want to mention that this was fixing general relativity and just testing lambda CDM. But of course, you can test modification of general relativity that changes the prediction that the gravitational wave luminosity distance is equal to the one of electromagnetic radiation. So in some models of dark energy, you can couple your scalar field to the gravitational waves, and this can change how your luminosity distance of the gravitational waves behaves. So you can either amplify your gravitational waves amplitude, or you can lower the gravitational wave amplitude, and this is something which with this method you can test. So with electromagnetic counterparts, with 17/17 in particular, this also constrains this kind of modification, but notice that it's 17/17, it's only redshift of 0.009. So it's only changing, it's only testing a region in which if your model is to explain dark energy, then what you want to do is you want to go to high redshift because these modifications accumulate with redshift. So having like spectral sirens constraining higher redshift, it's going to be much powerful, and that's also what you get when you do the analysis. I'm going to skip that. If there are questions, I can go later. But the bottom line is that doing this analysis of the mass distribution, you can get constraints which are stronger than 17/17, in fact, by an order of magnitude, just because you are probing this higher redshift. Now, in the second part of the talk, I want to touch base on a different topic, but which is related, very much related to the fact that gravitational waves are going to give us information of higher redshift. And when we go to higher redshift, we are going to, the probability that our sources encounter some matter distribution on the way is going to increase. So this is showing the optical depth as a function of redshift. So far, we are detecting essentially sources below redshift of 0.5, 0.6. This is the typical sources that we get now. So you see that for those, the optical depth is relatively, the probability of having lensing is relatively small. But then as we push to the next observing runs and next generation detectors, we are moving towards this higher redshift where the probability of having lensing is going to increase. So that's something very interesting to explore. And then, so in simple terms, when we are solving lensing, what we care about the geometry of our system. So massive objects will bend out the trajectories of light and gravitational waves. When we are analyzing lensing, the important parameters are of course the mass of the lens, the lens model in general, but also the geometry where the lens is located, and also the frequency of the source. So something which is interesting of gravitational waves is that their wavelengths are much larger than of astrophysical size, so you are much more likely to have a wave effect. So when you solve lensing, you need to take into account you have to solve diffraction integral, you look for all the paths of your wave, and then if your wavelength of your gravitational wave is of the same size of the size of the lens, then you can have wave effects. But this is just a note. For the rest of the talk, I'm going to focus on the regime of strong lensing. So this is the regime in which the time delay between the stationary points of this diffraction interval, in other words, the images, is larger than the period of your source. So this is something equivalent to what we are not very used to see, like these high redshift quasars, which have multiple images. So that's the regime in which we are going to be focusing on. In this regime, the diffraction integral simplifies a lot because it just essentially contains three terms. The first one is just the magnifications, tell us if our source is going to be magnified or demagnified. The second one is the time delay. Each of the images will arrive at our detectors at a different time. And also there is a phase shift that is going to affect the signal, as I will explain in a second. So in our detectors, what we will get is something like this. We will detect one signal, and this is just a toy example, but you will get one signal, the first one typically magnified, and then sometime later, this here I'm just tuning it to. So this is the same plot, but sometime later you can get another image. Now, something which is very different from gravitational waves to electromagnetic radiation is the fact that we have an excellent time resolution. So for us, like measuring time delays is really easy. And essentially we have like millisecond precision compared to when you think of quasar or things like that. But the con side of this is that our sky localization is terrible. So we are never going to resolve the angular position of the images. So if you make the order of magnitude calculation, the Einstein radius is of the order of arc second, and our sky localizations are of the order of tens of or hundreds of square degrees. So we are not going to see the different positions. For us, all the images will come from the same region of the sky. So we want to look for events that come from the same region of the sky. Now, this phase term that I was mentioning here is going to be very important in what comes next, because also with gravitational waves, we are sensitive, we detect coherently the wave. So we are sensitive to its phase. And then these phase shift that can have like discrete values depending on the image type, whether it's a minimum, a saddle point, or a maximum of the lensing potential. Anyway, this phase shift, what it's going to do is going to introduce a time delay, which is going to be different for different frequencies. So what that means is that if for a typical gravitational wave, which is composed of different modes, you just do a multipolar expansion, and the most dominant mode is the quadrupolar one, the 2-2 mode, but then you also have other modes that are more relevant, for example, if you have asymmetric masses. So each of these modes is going to be time shifted, if you want, by a different amount. So what this means is that our lens signal, the total lens signal, which will be the composition of all these lens higher modes, can display distortions. So
running this time delay if it's not proportional to the frequency.
Well, I mean, I'm just saying.
It just changes the shape of the. Why are you calling it time delay?
Well, at least to me, it's a good way of understanding where the distortion comes from. So there is no frequency. What I'm just doing is, if you can reinterpret this last term as a time delay. I mean, you just multiply and divide by frequency, and then that will be the equivalent. I mean, of course, I agree that
when you plot them, they're not because there's no frequency there, so they just have a different shape.
No, but I mean so each of the frequency of the frequency of each of the higher modes is different. So it's more. I mean, so for the quadrupole you have 2 times the orbital frequency omega. For the higher modes you can have like different multiples of that. So so at the end it's like, if you, I mean, it's just a way of, at least to me, that it's easy to interpret this, is that each of them is shifting in a different way, so that the overall signal, which is the interference of all of them, it has some distortions. Yeah, but I mean, strictly speaking, I mean, the time delay should be frequency independent. So,
Regarding the distortions.
Yeah.
So how distinguishable is that from just inferring the wrong parameters?
Excellent question. Yeah. So that's what you want to understand whenever you are trying to search for lensing just looking for this distortion. So the nice thing is that with this, if you see the distortions, you could say that this signal has been lensed only with one image. But of course, you need to see like how large is the distortion and if this can be mimicked by changing some of the parameters. So when you have like only quadrupolar radiation, this is completely degenerate with changing the coalescence phase. But there are also other combinations of the parameters that can mimic these distortions. So this plot, what it's showing is the signal to noise loss. So how much signal you lose compared to the optimal fit when you have different templates, which vary different some of the parameters. So the conclusion here from this plot, you see that in all the cases, the signal to noise loss is relatively small, which means that in general, we will need high signal to noise events to be able to see these distortions. And in fact, when you go to a catalog of events, what you see is that most of the signals are equal masses dominated by quadrupolar radiation. So at the moment, we don't expect to see these distortions, which is also good in the sense that it means that with our pipelines, I mean, we are not going to miss a lens event. But what means is that we will probably need to wait to next generation detectors to really identify these signals in this way. So if you are not seeing distortions, you can just look for multiple images just by looking for events that come from the same region of the sky, that have similar masses, that have similar spins, and that is what has been done by the LIGO-AMBITO collaboration, analysis I took part of, but also by other groups. We see that there is no evidence of lensing within our data. We are currently working on the second part of the third observing run. So there are more data that still needs to be analyzed. There has been some events that has some intriguing parameters that people here discovered first. But when you take into account all the astrophysical priors that we have, it seems unlikely that this particular pair end up being less. Yes.
When you sort of put the typical lensing separation up, you had in mind some scaling with 10 to the 12 solar masses. So you have in mind some sort of regular strong lensing by galaxies type halos.
Yeah.
What's the optical depth?
Yeah. So so that's my next plot. So this is not the optical depth, but this is the rate of lensing. This is a work, by the way, by Faye, a student at UChicago. So this is in terms of the velocity dispersion. So for galaxy lensing, typically it will be like around 200 kilometers per second. And then what you can see is that the rate for this, the rate of lensing is still below 1 for current detector sensitivity. So this means also that it's not surprising that we haven't detected yet lensing. I mean, it's within our expectations. But you see that if you move to other sensitivities, for example, at the same sensitivity of current detectors, you could have one event, and with a next generation, you could have hundreds of events. Now, the problem here is that as it happened with this pair that was identified, it's very likely within our data that just events, just by chance, they have similar parameters. So this is just a simulation of how the sky maps of a pair of events will look like, and this is just some in a mock catalog of events, just two random pairs that happen to overlap in the sky. So and the same thing happens for other parameters, just because as we increase our catalogs, the number of possible pairs increases with the n square. We will have many pairs that will look just by chance like lensing. And
That's
this,
not a good explanation for that event because that was computed, right?
what do you mean? Sorry, what?
For the particular event that we were saying,
Yes,
we did the Lucas-Ware effect and it was rare. So the thing is not well explained by this coincidence. It's also not well explained by lensing. I'm not claiming it's a lensing event. I mean, it's crazy that it's an lensing event, but it's also very unlikely to be a thing like that.
yeah.
I mean,
Well,
that's computed.
I think, I mean, I haven't done the analysis of that concrete pair. But I think at least for, I mean, when we do the number of false alarms in a typical in a catalog, I think we find that it's very common that you have like high overlaps in the parameters.
I mean, the event had many things in.
Yeah.
Obviously, right?
Yeah.
I mean, we are dumb, we are not, okay? And it is obvious that you could have such, coincidence, and we checked. And so, there's a problem with that check that we did. I'm happy to discuss, I'm doing better, but it's not that this thing, it's explained by this, because the whole point was trying to estimate how probable that is, and the Morse phase that agrees, and all of this stuff, and it was unlikely. Of course, lensing is also super unlikely. So I'm not claiming there's a good understanding of this event or that it's lensing, but everybody understands that the parameters can be.
Yeah, but
also this depends on the mass of the thing. Okay, anyway.
Right. I mean, but I think my only point here was that when you are doing searches, just searching for overlaps in parameters, you're gonna have many false alarms. I think that's the point that we are making in this paper. Yeah, I mean, maybe we can talk later. I mean, yeah, and I mean, and of course, this is just also if you are, I mean, so this problem of the false alarm is also if you want to be like super agnostic about your lens modeling. So for example, if you focus on the case of galaxy lensing, you have a typical time scale for your time delays. So you can cut like your catalog, you can say, okay, like time delays larger than a year is going to be very unlikely. So then, you this problem of having the number of pairs like a scale of with n squared, like you can solve part of that. But what I'm just saying is that if you're just looking for overlapping masses, overlaps in phase, overlaps in scale localization, that's something that happens very often, at least to what we see. Maybe just the last, well, this is not the last point, but something to say is that if once we have like confidence detection of lensing, it's interesting as a way of statistically probing the matter distribution in the universe, and the key parameter, I mean the key what you want to look for is the distribution of time delay. So because that's what we measure best, and that is something which is different can be different for example, different velocity dispersion, different type of masses of the lenses. So in this work by Fay, what she shows is that you can have some constraining power on the velocity dispersion just when you have like hundreds of lens events with the next generation. The last point is just that I was talking about distortions. We mentioned that there could be degeneracies with astrophysical parameters, but also there could be degeneracies with modifications of gravity, because like also many modifications of gravity, they just look at a modified dispersion relation. So this modified dispersion relation is going to change the phase of your wave. For some alphas, in particular for alpha 1, you get something which is exactly degenerate with lensing. For other alphas, you can get some partial degeneracies. So this is work in progress. I think that will be released very soon. But there is what you can see is that there is a regime in your signal to noise in which you could say, okay, my lens general relativity waveform is not fitting well my signal, and your modified gravity is fitting better the signal. So this is just also kind of as a warning for the people who are doing like test of general relativity, that also they should look just in case they should test also the lensing distortions to be sure that they are not being full.
Presumably those regions of parameter space in your modified gravity theory are already constrained through like propagation or like generation.
Yeah, so
lensing is such it's a relatively sub-leading effect. So
no, but I mean there are it's not there are modifications of gravity which are still allowed that will look like lensing. Then what this will be a degeneracy only on our event, on one event if you want. Of course, if you analyze all the events, modified gravity should affect to all of them. And lensing also should affect to all of them, but in a different way, because it comes with the optical depth, and modified gravity will come with the properties of whatever modification of gravity you have. So these degeneracies are, of course, only on a single event by event basis. When you do a population analysis, they should be broken. But still, I think it's just, I mean, if we, I mean, as we have higher signal, as we are going to improve our sensitivity, we're going to see distortions, just also because our waveforms are not perfect. So it's just kind of like a warning that we should also, I mean, when we are, but for people doing modified gravity, this has to be taken into account.
Do you have a sense of what kind of theories that would affect? I mean, here, as far as I see, your approach was agnostic in a way that it was just parameterized by some parameter alpha.
Yeah, so so this parameter alpha, if it's 0, this will be like a massive graviton. If it's like 4, this comes in some Lorentz violating theories. So yeah, you can do some mappings, and there is a lot of industry doing that. Yeah, so but yeah, it depends. Also, like in general, like a full theory, modified theory of gravity will not only change the phase, it will also change the amplitude, as I was mentioning before, and it can change other things. So in fact, I mean, you should do like all the analysis together. But just because now people are looking for distortions in this way, changing the dispersion relation, that's something that could have some degeneracy. So I think this is all I wanted to say. I can leave you here with my conclusion, and I'm happy to take more questions. Yeah. Thank you.
So I have a question about coherent lensing. So
Yeah.
there are these interesting events that are super, super high mass, which people have speculated come from 2+2 systems that merged first and then merged together.
Yeah.
And so then we conceivably should be able to see events where 2 smaller mass black holes are merging, and there is another black hole in these, you know, triple systems, quadruple systems. So then is that the regime, would that be the regime of coherent lensing, or and then my question, or do you have something completely different in mind for like coherent lensing in terms of when that would dominate? And my other question is, would we even detect them now, right? Because we do these detections by template matching. So if they are coherently lensed and not recognizable through standard templates, are they recognizable in the data?
Right. So there are searches that look for these wave effects or microlensing effects in the waveform. In fact, that's something which I'm thinking with a student of computing. I don't know the probability, for example, in a cluster of having lensing being relevant. What has been done, for example, is in the case of binaries forming in an AGN disk, and then like having lensing with the supermassive black hole in the middle. That's something which has been explored, but it's different from the situation you said. Typically, also bear in mind that I mean, if both masses are comparable, like the wave effects are kind of small, so you have larger effects when for example, if you have a 30-30 solar mass binary, and then this is lensed by a 1,000 solar mass black hole. I mean, if you have 100 solar mass black hole, yeah, maybe you could also have some wave effects. But I think the important thing is to compute the probability of that, and I don't have that number in my head because we are actively working on it.
if you add like dark sirens to the first like part you were mentioning, does that break more degeneracies or?
Sorry, what?
Like if you add dark siren method of like cosmology, does
Yeah.
that like break more degeneracies?
Yeah, that's a good point. Yeah, of course, like for the events which are very well localized, like you want to also use some extra information, but I think it's important like not to get biased in the sense of I mean from the completeness of your catalog. So that because that introduces some difficulties there. So I think like I see at least like bright sirens, those with an electromagnetic counterpart, as being like the primary way in which a gravitational waves are going to constrain H naught. And then these spectral sirens will be more constraining, will be the way that we will have to go like beyond redshift 1 and constraining the expansion rate at high redshift. And then dark sirens are a bit like in between, but yeah.
Yes, go ahead.
You have a coincident lensing with a counterpart?
Yes. I mean that could happen, and like as we you see, like for example, well, in my first slide, you can detect like binary neutron stars with next generation detectors up to redshift 2 or more. So that means that you will see binary neutron stars. But then the question is, what is the if you are? I think like for those high redshift, detecting the short gamma reverse is kind of challenging to localize. Maybe if you have a binary neutron star at redshift 1, you could do something like that. But related to that point, also something which is important, and I think related to identifying and confidently claiming lensing, is that you can also, if you have some, the group here did, like when you have a candidate for lensing from gravitational wave, you should also go to your electromagnetic data and see, like, okay, do we have clusters there? Do we have any source which is being lensed? So I think in order to have like confidence detection of lensing, apart from the waveform distortions in the type 2 images, which is very singular, I think we will need to very likely rely on additional electromagnetic data.
I mean, you have the time delays and you have the type of the images. So I think it's and the magnification of the images. So you can easily know if that particular, the lensing galaxy example that you have there corresponds to the gravitational wave. So I think it's not, given the optical depth that he was showing, it's not crazy that a big fraction of this lensing you will have found the counterpart, that you will know the redshift without any kind of, without an electromagnetic counterpart matching.
More questions? Are there any questions from the Zoom? I don't see any. Okay, let's thank Jose again. Let me just remind you that Jose is staying with us today and tomorrow, so he still has many like spots in the spreadsheet. So please subscribe for one-to-one meetings. And also, we're going to dinner tonight at 6. So if you're interested, please let me know.
Thank you.
Oh, you're here. The meeting at 2.
Great, okay, I can just leave it.
Yeah,
just leave it. You might have to go to lunch and start discussing it. Very nice talk.
I'm not sure if I can read that before.
I mean, it's just
Afterwards.
for
Okay, definitely, definitely, yeah, I'm very interested. I'm just like, yeah, sure, I think that's very cool. So our prediction probably will see very eccentric distribution.
Right, our answer, and I also thought you said in your paper that for closed memories, closer memories, that we have more uniform. And uniform distribution.
Yeah.
Do you think this is the case that you have
My feeling is that that's a little bit difficult because human random pair is a little bit difficult to random pair with the just a certain velocity.
So you think that
Yeah, I think it's more, and also other separation or other interaction can be very important. Like other time we have a planetary disk, and probably this cause finance outform of the disk. So yeah, it becomes quite common. So it's not just like that. No, I would say that.
and not on the knowledge.
So I think from simulation they do have some plots that look sort of like more or less uniform, but I can send you the plot, but I don't think they really plot the distribution, and also suspect they are not super confident in that. But we can see that, yeah, I can see the plot. So it's also the simulation from Matthew Wade. I think they don't care that much before because that's not major. Yeah, that's not yet measurable. But right now, I think it's getting more.
So you're like reading this.
Hopefully, yeah. Yeah. So I would say there are a lot of explore change this stuff. So actually, right now, I think my next paper is probably related to like. So now we just focus on the entire binary population. But if you select some population, for example, select certain mass ratio or certain mass age, yeah, so everything is still not necessary. Yeah, that's also something. That would be very cool. So, yeah, I think that would be very interesting if we turn out to see very eccentric. Yeah. I think that would be
I think you said, yeah, I mean, the outside expression.
I'll look into that. So I think so far I checked Horus, and Horus doesn't look that great, but I think partial